Welcome to our NPTEL courses on advanced power electronics and control. We shall continue with the non-isolated DC-to-DC converter. We are discussing about with the boost converter. So, we continue with that boost converter. So, in a boost converter essentially you will be boosting the voltage, and since actually one switch is on, so current input current will ramp on through the switch, and when switch is off, then there will be a stored inductance, there will be a value voltage VL will appear across it, and this voltage and Vs will basically fit the load, and thus you will find that the voltage applied across this load has enhanced. So, this type of converter circuit, inductor is connected in series with the supply and switch is in a parallel with the supply. Diode is connected with the series of the load to avoid the backfeeding. Here the load inductance is assumed to be very small. Switch S is on at t equal to 0 during the interval 0 to t on, and output voltage should be equal to 0 because you have shorted the switch. The current on the source Is flows through the inductance L. In this interval, value of the current increases linearly. So, since di dt is positive and the equation is Vs equal to L di dt, ignoring that actually switch is on, the drop across the switch is almost 0. So, you will get Vs by L as a ramp of this di dt. So, when switch is off, during that period actually t is less than capital T to t on, the current through the inductor decreases with the same direction of the current, since it is a DC to DC converter. So, ultimately the Vs equal to V 0 plus L di dt. So, here you will find that actually ds dt equal to Vs minus V 0 by L. So, as shown in the waveform, the current varies linearly I 1 to I 2, that is I mean to I max during the t on interval, that is actually I 2 minus I 1 equal to I max minus I mean, that is essentially Vs by L into the time on, the duty cycle when switch is on. Similarly, current varies linearly from I 2 to I 1 during the t off. So, di dt can be expressed as follows. So, I 2 minus I 1 equal to I max minus I mean equal to V 0 minus Vs by L into t off. So, we can equate both the equation I 2 equal to I 1, and ultimately we can get actually V 0 equal to Vs 1 by 1 minus k, and since k equal to t on by t, you can substitute that value. Actually sometime it is written as 1 by 1 minus d, where d is also same as k. So, the source current is assumed to be continuous and it is in a CCM mode. Output voltage is higher than input voltage. For this it is called the boost converter. Instead of the commutator device thyristor is used, it is called the step up chopper. So, we can see that when actually it is, when we require a regenerative braking in the DC motor. So, we use this kind of applications called step up chopper. So, now let us come to the another topology, that is whether you can step up as well as the step down. There will be a position change, please note that change of the position from the switch. So, we have to have a, we can choose a, so when you have to switch will be in this position in series with the load, and inductor will be placed, when actually in parallel to the load, and thus when it is switches on, essentially this gives you the boost topology, because here there is an inductor and there is a switch, and here it is just interchanged. But another point to note that this actually polarity of the diode. Polarity of the diode is reverse. Generally in boost topology you will find that polarity is just opposite. So, how does it work? You may require to boost the voltage or you may require to buck the voltage depending on the different kind of requirement. Mostly it is required in case of the variable DC supply and you are going to feed a constant DC voltage, and that kind of applications where we may require to buck or boost the DC voltage. So, what happen initially, if it is switch on, this is same as your boost operation, and thereafter you will have, when it is switch off, then energy stored into the inductor will feed and ultimately current will flow through like this, and then essentially you will have a buck operation. You recall this, actually switch off part of the buck, you will have the same topology, but here this inductor was placed here and diode was placed in this position, just this has been interchanged. So, you just couple these two and ultimately you come out with this topology called buck boost. Let us see that how you have a principle of operation of the buck boost topology. In this converter circuit, inductor is used in parallel with the supply, please note that. So, in boost topology it is nothing but a boost topology when it is switches on, but position of the inductor under the switch has been interchanged. That is connected with the series with the load, but polarity is opposite. Generally you require a constant DC voltage. To hold that DC voltage, you will have a capacitor is connected with the parallel to the load, which is not shown in the previous figure. Polarity of the voltage is in opposite of the voltage as shown in the previous figure. When switch is on, the supply current Is flow through Vs Is L during the interval T on. The current through both source and inductor IL increases. So, dIdt is positive. Polarity of induced voltage is same that of the input voltage. So, the equation of the circuit can be Vs equal to L dIdt. So, dIdt equal to Vs by L. When S is off, inductor current tend to decrease with the slope, and that is basically then it will be minus dIdt. So, this is the case. Now, essentially let us see the polarity of DC voltage is opposite of the Vs and the current path is through the inductor L, parallel combination of the load C and the diode during the turn off interval. The output voltage remains nearly constant as the capacitor connected across the load will hold the voltage, and so the equation becomes L dIdt equal to V0 and thus dIL dt equal to V0 by L. Inductor current varies linearly with IL1 to IL2 during the T on interval, and IL1 is considered as IL mean and IL2 is considered as IL max, same in case of the boost converter. So, dIdt expression can be rewritten as IL2 minus IL1 equal to Vs by L into T on. So, similarly we have to write the equation for the T off interval. So, inductor current varies from IL2 to IL1. So, L dIdt can be expressed as dIdt can be expressed as IL2 minus IL1 V0 by VL into T off, and equating both the equations V0 equal to Vs T on by T off. Similarly, again you can write V0 equal to Vs K 1 by K 1 minus K, where K equal to T on by T. So, you know that T equal to T on plus T off. So, ultimately you get these expressions as the transfer function. So, V0 equal to Vs k by 1 minus k. So, at duty ratio 0.5, so you can find that. So, output and the input are the same. So, for duty ratio less than 0.5, it will operate as a buck converter, and duty ratio above 0.5, it will act as a boost converter. But mind it, there is this ratio actually increases quite non-linearly, because actually you can take the value of 0.6. So, what will be actually the value of this transfer function? So, it is 0.6 by 0.4. So, it will be actually 3 by 2. If it is 0.8, then it is 0.8 by 0.2, it is 4. So, it will increase quite drastically. So, this is one of the actually challenge. Increase of the voltage is not proportional with the duty cycle. So, from the output voltage expression, it can be observed that the value of k, if it is 0.5 to 0, the output voltage is lower than the input voltage. So, it will act as a buck converter. Similarly, if it is above it, so output voltage expression is observed that for k more than 0.5 to 1, it will be actually using as a boost converter. So, it is observed that for k less than 0.5 and greater than 0, output voltage is lower than the input voltage. So, it will be a buck converter. When actually k is less than 0.5 and 0, output is 1, the output voltage is higher than the input voltage. So, it acts as a boost converter. Therefore, the different value of the different k value of the converter is considered as for the buck boost converter. Here inductor current is assumed to be continuous. Also, it can be termed as a step up step down chopper, since it can have a buck boost properties. Now, we shall see that how we will control this output voltages. So, all the 3 types of DC to DC converter, average value of the output voltage can be varied by time ratio control. We will see that we have already discussed some control strategies in case of the PWM converter, and also the current limit control. So, time ratio control is essentially the control of the duty cycle, and we will assume that if it is not stated, current is continuous. So, our assumption is quite simple. So, load current is continuous. So, we shall discuss later, and otherwise we will state that it is a discontinuous mode of operation. Here the value of the duty ratio k equal to T on by T, and of course, this we have derived this expression, we have taken the continuous load current. It is also classified into 2 types: constant frequency operations and the variable frequency operation. So, in the constant frequency operation, frequency of this converter remains constant. So, you have a ease of designing the circuit. What happen, you can choose a particular switch, because that actually if you have a higher switching frequency, then you require to use MOSFET, but it has to reduce the power rating. So, choosing a switch, thereafter choosing the frequency, all those issues will come, and if you know that actually the constant frequency is constant, then design will be easier for choosing the switch as well as the design of the inductor and capacitor. But you will pay penalty somewhere else. We will see that actually the stability and other issues. And another is the variable frequency operation. So, hysteresis control and other control are the variable frequency operations. There you will change the duty cycles, there will change the frequency, and you may have a constant T on also. So, there we can have a change the frequency and we will have a actually variable frequency operation. In constant frequency in this control, that is constant frequency operation, strategy T on is varied keeping the frequency overall frequency kept actually 1 by T constant or whole time period is constant, and this is also called pulse width modulation control. Now, what happened, this is the load voltage and you will actually this is the value for k equal to 0.5, 0.25 and this much will be the T on and this much will be the T off. So, ultimately this will be the average voltage and this is for the variation of the T on. T on is varied for 0.75 and you can see that this is the pulses. So, this is called constant frequency operation with varying T on. Now, let us come to the variable frequency operation. In this control strategy, the time period T is varied either keeping T on or the T off constant, and it is called also the frequency modulation control. The output voltage is varied by varying the duty ratio T on by T or T off by T, whichever is a constant. So, there are few disadvantage of variable frequency operation, because I told you, we require to design the converter for the particular frequency depending on the switch and the inductor and the other devices. So, that becomes a challenge. Here control output voltage, here to control the output voltage frequency has to be varied in wide range and for which the filter design will be difficult. For this control strategy, to control the duty ratio, frequency variation would be wide. In this case, this possibility of interface of some other frequencies also come into the picture, and ultimately you may have a high spectrum and it may interfere with the other high frequencies component, and that may gives you actually issues of the EMI EMCs. And large uptime of this control technique may lead to the discontinuous current, and which is undesirable. Current become peaky and you have a high EMI EMC problems, and whatever expression we have derived, that nothing is applicable in case of the discontinuous conduction mode. We require to recalculate all the expressions and the duty cycles, and therefore, constant strategy control is more desirable, but sometimes we will require to force to use a variable frequency operation because of ease of control. So, what happened, therefore, constant frequency control strategy is more desirable. So, this is actually constant T on. So, you make the T on constant and you vary the frequency, and accordingly actually the voltage changes, and here you vary you make actually T off constant and you vary the T on, the duty cycle changes. So, these are the two strategies for the variable frequency operation. Now, we come to the another control strategy, that is called the current limit control. Please note that you got dIdt, which is positive in case of the boost control converter. So, current is ramping on. It is any case when your current is on, when switch is on, all those DC to DC converter we have discussed, current ramps on and current is ramp on through the switch. So, we require to actually limit the switch, because switch has a limited capability of carrying current. So, that is said to be the current limit control. So, you will allow to current to ramp on, and it will actually transfer the energy until it hits the current limit, you will switch off it. So, automatically you will have, you essentially these two methods is deals with the output voltage. It does not take any input of the input current. But while changing this, actually this frequencies, what happen, your while changing this, actually the t on time, keeping t constant, you may actually cross the limit of the current which has been prescribed by the switch you have chosen. So, and you may ultimately leads to the damage of the switches. But in this case, there is no possibility of the damages of the switches, because you are basically protecting the devices from the having high inrush current, and you are controlling the current. All type of DC to DC converter, current is assumed to be continuous. That is what our thumb rule. The current limit control strategy, the switch of the DC to DC converter, when it is turned on and turned off, that maintains the current is actually switches between, as we have seen, upper and the lower limit of the current. That is basically maintained between the upper and the lower limit. When current exceeds the maximum limit S, then switch will turn off, and when current goes down to the below the minimum limit, it will turn on. It is just will operate in a band of the hysteresis. It's like your AC will turn on, if you are setting the switch, let us say 25 degree centigrade, when it will turn on, let us say it is 25.2, again it will continue to chill down, and while the actually your temperature goes below, let us say 24.8, it will again turn off. So, your bandwidth is basically 4 degree. So, it is something like this. This type of control is either possible with the constant T on or constant frequency. We can do either of it. So, generally we will prefer constant frequency. So, we will have a ease of designing the component as well as the choice of the switches. The type of control, this type of control is possible when load is inductive. So, please note that when actually you have these issues that come into the picture, and this type of control strategy reduces the ripple current with increasing the switching frequency and the switching losses. So, ultimately you will have a band IL and the I max, you will be restricting it to the I mean and I max, and ultimately you will have the switches, that is I max and I mean. So, T on will be there when it is ramp on. Once actually it is hit at I max, again it will come down and it will be following, like continuously it will follow. Now, while discussing this control strategy, we shall apply this into the buck converter, and it is quite relevant. We have taken a RLE load. It may be so that a buck converter or the buck chopper, it is feeding a DC motor, separately excited DC motor. So, where this is basically R can be the armature resistance, and this is the inductance part, there is a field part of it that is giving to the LA, and you got an back EMF because motor is rotating and gives you a constant voltage. So, you can have something like this, or you may be charging the battery. So, that kind of application also we can model as a RLE load. So, we have already discussed various type of DC to DC converter. Now, let us discuss the buck converter. The output voltage and current of the DC to DC converter and the strategies already been discussed. So, in this lecture detailed analysis of the buck control converter with RL load, RL and the back EMF or the battery has been considered, and thyristors as a switching device has been discussed. So, and this since it is a thyristors, actually we require to have a force commutations, otherwise it will continue to flow. So, you give a gate pulse, and if it is actually and it will be trigger it on, thereafter you may off basically the you may off this basically the gate current, and current will ramp on. But if it is instead of this thyristors, if it is other devices like IGBT, you require to actually give a continuously gate voltage or gate current. So, current will flow like this, and accordingly actually the load will get the voltage Vs, and where this dotted line corresponds to the value of the back EMF or the battery voltage. So, here you have triggered it off by by force commutations, or if it is IGBT, then by actually the switches by the withdrawing the gate pulses. Then what will happen? Then voltage, load voltage will come down, and ultimately since you got a freewheeling diode, ultimately current will take this shape and no voltage will be appearing to it. And if it is actually commutated, if it is actually this discontinuous mode of conduction and current becomes 0 at this point, then again we have a motor inertia that will be in second, and these phenomena are in microsecond. Sorry, this phenomena is in millisecond. For this again the voltage will be built up to the value of E. Again this thyristors is triggered, and ultimately current will flow like this. Please note that this is basically the current through the thyristor. So, if you have a, if the load current is continuous, then actually back EMF will be not manifested in the load, or the battery voltage will not be manifested. You got this kind of waveform in a continuous load current, and this will be the discontinuous load current. So, let us say, see what we have observed. The procedure of finding the maximum and the minimum value of the load current, assuming the continuous conduction mode, is required to be discussed here, and we will find out the equations based on the continuous conduction mode or critical conduction mode. There are two modes of operation. During mode 1, when t equal to 0, thyristors is on, DF is off till t equal to T on. During this period, the load current increases. The induced EMF across the inductor is positive, having the same polarity as that of the input voltage opposing it. Mode 2 will start off by commutations of the thyristors, and t equal to T on, thyristors get turned off by the auxiliary circuits. We have auxiliary commutation circuits, and DF get turn on, and so the load current start decreasing, and the induced EMF across the inductor changes its polarity, and this period voltage across the diode become positive till t equal to capital T, or the complete of the duration. So, we shall write the equation for the T on when switch is on. This equation of the load current during this interval is Vs equal to R I 0 plus L d I 0 plus back EMF. So, you can take the back EMF or the battery voltage in this part, and you can rewrite these equations, and we can solve this equation. Ultimately, it will be a first order differential equation, and the first order any differential equation are the initial value problem. So, we get to find it out the constant A and B. The current in the load current is same as the source current during this interval. The values of the load current I0 at t equal to 0 and at t equal to t on are I mean and I max respectively. So, at the beginning it was I mean, so it will go up to the I max. So, ultimately we can find it out at t equal to 0. So, that is A plus B equal to I mean, and at t equal to infinity that value equal to I0, that value equal to B. So, B minus B by R. So, and so A become I mean minus B minus E by R. So, you can substitute these results. So, the whole equation becomes I0 Vs minus E by R 1 minus T by tau plus where tau is the actually T on. So, I mean e to the power T by tau. So, at T on, so I0 equal to I max. So, you can substitute that value of the I max here Vs minus E by R 1 minus T by, instead of the tau you just substitute T on by. So, you get this expressions I max by I mean equal to Vs minus E by R 1 minus T on by tau. So, this is the equations for mode 1. Mode 2 just actually it will start from the I max and actually end at I mean. So, same equations, but you do not have any input voltage. So, I0 plus L di dt plus E. So, you can rewrite this equation like this. Same way you can have a solutions of the load current m square. So, we can actually get t equal to 0. So, that value equal to A plus B equal to I max. At t equal to infinity it will be actually B minus E by R. So, while substituting you can get the value actually minus E by R 1 minus e to the power minus T by tau plus I mean e to the power minus T by tau. So, once you write these equations actually you get I max e to the power T up by tau minus I mean equal to minus E by R 1 minus T up by tau. So, you just equate, since I max and I mean are the boundary condition, they are same. So, this second expression is obtained mode 2 between I max and I mean. So, for these two expressions you can equate. So, I max equal to Vs by R 1 minus T on by tau 1 minus T by tau minus E by R, or you have these expressions. Similarly, I mean you can have the expression Vs by R T on by tau 1 minus e to the power T by tau minus 1, or you can have these expressions. So, these are the actually the current varying between I max and I mean in case of the step down chopper with the thyristors or the buck converter feeding RLE load. And now, let us analyze the buck chopper for the concept of the ripple current, because we want a steady state current. We have seen that while turn on actually current goes to the I max, thereafter it is coming to the I mean for the continuous conduction mode, and this is the waveform for the critically conduction mode. Now, as we have talked about, that load current varies between the maximum and the minimum values. If I mean touches 0, then we will say that it is in a critical conduction mode. Therefore, from this previous analysis we can write that what should be the content of the ripple, that means that actually del I, that is equal to I max minus I mean. So, you can substitute, you can subtract I max minus I mean, we have gotten expressions of I max and I mean, that is Vs by R 1 minus e to the power T on by tau into 1 minus e to the power T minus T on by tau by 1 minus e to the power T by tau, and if you simplify multiply these equations, so essentially you get Vs by R 1 minus e to the power T on by tau into 1 minus e to the power t of by tau by 1 minus e to the power t by tau. Now, if you can investigate these equations, let us put k is this basically the duty cycle. So, k is the duty cycle and that is T on by T, and the expression becomes actually Vs by R 1 minus T minus kT by tau 1 minus kT, that is basically T of by tau by T. So, essentially its per unit ripple value, if you say in terms of the percentage, it is I max minus I mean by actually the average value, that is nothing but Vs by R. It will be basically that will depend on 1 minus e to the power kT by tau into 1 minus 1 k t by tau by 1 minus e to the power t by tau. Now, accordingly you can see that the value of this I max minus I mean will actually vary in by these equations. So, thank you for your attention. In next class we shall continue with the different kind isolated converter and the different kind of chopper in the next class. Thank you.